Welcome to Astrophiz. My name is Brendan O'Brien and Astrophiz is produced on Yorta Yorta, Pangarang and Kahuna country. We celebrate the first astronomers of this land. Monthly, we explore the universe with the world's leading scientists. For transcripts and more, visit astrophiz.com. And here is Dr. Ian Musgrave with your September Sky Guide. Hello, Ian.
Hello, Brendan.
Great to be speaking with you again, Ian. It's been a fabulous year. Can you tell us what's up in the sky for September?
Okay, well, there's going to be a lot of interesting things in September. Now, the planetary action has returned mostly to the evening skies, although the morning skies are still putting on a bit of a show. Venus, which has been our companion for many months, is now starting to sink in the late twilight. Then Mercury returns to the evening sky later in the month below Venus, and you will see some interesting interactions between Mercury and Venus. Saturn is now well visible in the evening sky, but still visible in the morning sky. And Jupiter enters the morning sky below Mars. So let's talk about it in a bit more detail. So the first off, the Earth is at spring equinox on the 23rd. For those of you who listening to this in the Northern Hemisphere, of course, that's autumn equinox. The moon is our guide for many of these things. So September the 4th is the last quarter, which is ideal for stargazing in the evening. September 11th is the new moon, which is also ideal for stargazing. September 19th is the first quarter moon. Now, this is an apogee first quarter moon. If earlier in the year you took some photographs of the perigee first quarter moon, when the moon was closest to the Earth, taking some photographs of the apogee first quarter moon is going to get you a nice little comparison of the differences in size between the moon. We tend to talk in terms of supermoons and mini-moons, but it's important to realise that perigee and apogee also occur at all moon phases. And a perigee new moon you can't see, not very exciting, but a perigee first quarter moon is easy to see early in the evening. And again, you see this difference in size between the two moons, and it's very interesting. And then on September the 27th, there's a full moon, which is a fairly ordinary full moon, but still very nice, let me tell you. The moon is at perigee on September the 7th, as we said, and at apogee on September the 19th. Now, let's have a look at the planets in the skies. As I said, Mercury enters the evening twilight late in the month, and from the 16th, it can be seen low above the western horizon. You'll probably need a fairly low and level western horizon to see it easily. And it forms a line with Spica and Venus, but then it starts rising rapidly into the evening sky. It will be at its best next month, but this will be a harbinger of what we'll see next month. And on the 26th, Mercury will be less than a degree from the first magnitude Spica. That's the brightest star in Virgo, with Venus above it. Looking very nice in the mid-twilight. Now, Venus is now sinking in the evening sky. It was at its greatest distance from the sun late last month, but now it's beginning to sink. It's still in Virgo and well visible after the sky is fully dark at the beginning of the month, and it starts entering nautical twilight later on in the month. If you're looking through a telescope, Venus is a distinct crescent moon, and the crescent becomes more and more obvious as the month goes on. Even in small telescopes, we also know that the Venus is apparently becoming bigger and bigger as this goes on. Now, I mentioned Spica and Mercury earlier on, but for the first couple of days of September, Venus will be less than 2 degrees from Spica. And then on the 14th, Venus is 2 degrees from the 4-day-old waxing crescent moon. If you remember the Venus crescent moon conjunction in August, it was a very impressive sight, and it'll be also another good time to try and see Venus in the daylight. Because on the 19th, Venus is at its greatest brilliance, around about minus 4.5 magnitude. It's incredibly brilliant, relatively easy to see in the daylight, but when you've got a obvious guide like the crescent moon, it'll be incredibly easy to see. And also, don't forget, make sure you've got the sun blocked out by something like a building or other large bulky objects, so you don't have any chance of destroying your eyesight by looking at the sun accidentally. Now, with Venus glowing in the west, Saturn is rising east, higher ahead of the opposition next month. Now, next month it will be biggest and brightest as seen from Earth, but even now, Saturn is an excellent sight in small telescopes. So at the beginning of the month, it's rising about 8:30 p.m. and is highest about 2:30 a.m. Mid-month, it's rising around astronomical twilight and is highest around 1:30 p.m. And by the end of the month, it's rising before the sun sets and is highest around midnight. Then on December the 27th, the moon is only 6 degrees from Saturn, making it very easy to find if you haven't been able to work out which bright object above the eastern horizon is Saturn. Saturn is basically the only really bright object there. And through a small telescope, the rings have been steadily widening from the very thin apparition of last year. Now, let's go back to the morning sky. Mars is still very obvious above the eastern horizon at astronomical twilight. That's an hour and a half after sunrise. It's in Gemini, passing through the body of the twins. And on the 7th, it's about 4 degrees south of the waning crescent moon. So, again, this will look very nice in the early morning. You may need an unobstructed horizon to see it to its best, but it'll be very nice. Now, Saturn's still in the morning skies, and as I said, in the early part of the month, it's highest around about 2 p.m. So for most of this month, Saturn, at least in the very wee hours of the morning, Saturn will be nicely visible and probably best placed for telescopic observation, even though it'll still be very good in the evening. But it can be seen that it's sinking lower and lower west. Now, Jupiter is entering the morning sky, and it is low above the horizon, although on the 9th, the planet will be around 2 degrees from the 27-day-old waning crescent. It's very low above the horizon in the twilight, and you'll need a flat, level horizon without any large trees or things to be able to see it properly.
Yep.
Now, by the end of the month, it's still low, although higher, but more readily seen. Those are the planets. Now, Coronae Borealis, guess what? It still hasn't gone bang.
Oh, no.
Oh, no, yes. Now, in our last podcast, I did not talk about Comet 220P, McNaught, because its outburst occurred after the podcast went to air. But Comet 220P has undergone an incredible outburst. It's zoomed up almost 7,000 times in brightness, a telescopically only visible in around about 7th magnitude, and it's done it twice. We're on the second burst now. It's still relatively bright. By relatively bright, I mean you need very strong binoculars or a telescope to see it, but it's somewhere around about magnitude 8 to 9. It may even be magnitude 7, depending on doing it. It's readily visible in the early morning. So I put out some spotters charts last month in August. It will still be valid because it's not moving very far. And I've been getting some nice images from the remote telescope at Siding Spring, but you won't see it anywhere near as excitingly. It'll be a dim dot, but it's worthwhile having a look at if it still hasn't faded too much. And it might even have another outburst. So, just keep an eye out. It could be very interesting.
Cool.
Now, the other thing that's going on, well, maybe it is cool. I'm just going, it's looking quite amazing. But the other thing that's going to be happening this month is an occultation of Antares. This is on Tuesday, September the 17th to 18th. Now, this is a good occultation in the sense that it's approaching first quarter, so you'll be able to see Antares disappear behind the dark rim of the moon without light of the moon getting too much in the way. It's a bad occultation because it'll be quite low to the horizon, so you'll need a clear and level horizon in order to see it. The moon will be obvious, Antares will be obvious. And if you're looking a bit before midnight or half an hour before midnight in the case of Adelaide, you'll be able to see the dark limb of the moon, possibly in Earthshine, crossing in front of bright Antares. Brisbane misses out, Darwin misses out, Sydney and Perth miss out, but Adelaide, Canberra, Hobart, and Melbourne all get to see Antares wink out, and then the moon sets before you can see it come back again.
Nice.
Yeah. So as you can tell from the occultation story, Scorpius is now heading westward and is setting roughly around midnight, but it's still high in the sky after astronomical twilight. Sagittarius in the heart of the Milky Way is at the zenith from about 8 p.m. And so it's a good time to go out with a lawn chair, pair of binoculars, and search around the teapot of Sagittarius for all the wonderful clusters that are around there. The magnificent globular cluster M28 is at its highest at this time, just off from the lid of the teapot of Sagittarius. But its rival Omega Centauri is setting, but it's still quite high and readily visible. And the other magnificent globular cluster of the southern hemisphere, or indeed the entire sky, 47 Tucanae, is rising. So these three globular clusters form a broad triangle and get across the southern sky. Now, they're quite faint, but if you're out in the depths of the countryside with nice dark skies, you can see these faint positive dots forming a nice triangle encompassing a large chunk of the southern sky. The winter triangle, which I talked about last podcast, of Deneb, Vega, and Altair, is very clear in the north. So we've got two triangles, the winter triangle of bright stars and the summer triangle of faint globular clusters. Both are equally interesting. Now, by mid-month, the classical Andromeda galaxy is seen low above the northern horizon. And in the south, the two dwarf galaxies, the Magellanic Clouds, are rising with the southern Magellanic Cloud almost at its highest. So we've not only got the two competing triangles, but we've got competing galaxies. Now, for a lot of us, the Andromeda galaxy is quite low. You may need binoculars to see it if you're in the suburbs, just low above the northern horizon, but it's still quite interesting in binoculars, and it can be seen as a faint fuzzy patch if you're out under dark skies. Now, our friend the Southern Cross is about at the 4 o'clock position as it heads southwards. It doesn't really set from most of Australia, although it does set in Darwin and not completely. The pointers are above. Now, the pointers can be used not only to point to the Southern Cross itself, but if you look a bit to the south of the pointers, you see a triangle. This is the constellation Triangulum Australe.
Yep.
And then if you follow the point of the triangle up, you'll see a blocky rectangle. This is the constellation of Ara, the Altar. Now, these unprepossessing, not incredibly bright constellations, but there's some nice little clusters near these constellations, and so it's worth getting out your binoculars and scanning around them just to have a look.
Yep.
And that's the sky for September. Lots of things to see.
Thank you very much. And now we're recording a week earlier than we would normally because I have to head up to Sydney because my daughter's running in the Sydney Marathon. And so we had to record a bit earlier, and I may not have given you enough time to develop a tangent. But Ian, do you have a tangent for us?
Indeed, I do. And it's a quite interesting tangent.
Cool.
I'm going a bit into history here but it's very relevant to what we're seeing. As I said, Venus is beginning to sink back towards the horizon as becoming bigger and brighter and becoming more of a crescent. Now, over 1,000 years, this was a bit of a puzzle to people. Why did all the other classical planets be seen throughout the night, but only Venus and Mercury stayed close to the sun? Now, the history of astronomy is often portrayed very simply. You have Ptolemy and his Almagest with his geocentric system, and then along comes Copernicus with heliocentric system. There's a bit of argy-bargy with Galileo and then Kepler. Then we have the heliocentric system we know today, but it's never quite as simple as that. Now, Ptolemy solved the why Venus and Mercury don't get far from the sun with a series of complicated circular motions, the epicycles, to keep them these planets apparently close to the sun, while the rest of the planets got very far away from the sun. Now, when we're talking about the history of astronomy, this is all before there were telescopes. All the observations were done by eye, and when they were constructing their cosmology, they had their observations, obviously, but then they brought in this extra baggage. So orbits had to be circular. The reason for this was that the heavens were perfect and the orbits had to be perfect, and the most perfect figure was the circle. Now, we may argue about that, but this was one of the governing ideas at the time. And Ptolemy synthesized the observations of centuries beforehand into this beautiful system, Earth-centered, because Earth had to be the center because the heavens were this incorruptible heavenly matter, and Earth was corruptible, and all corruptible things fell towards the Earth, and the heavens were outside the Earth. And you had this series of shells where you had first the moon, then the sun, then Venus, then Mercury, Venus, Mars, Jupiter, Saturn. In some versions, because once, as I said, we think Ptolemy, Copernicus, we forget that there were lots of other astronomers, lots of other groups, and they continually fiddled around with Ptolemy's system, because even though Ptolemy was seen as one of the pinnacles of astronomy, people went, yeah, this is the best, this is fantastic, but we could make it better. And so some other models had Earth at the center, then Moon, then Mercury and Venus, then the Sun, and then the outer planets. Again, because we know today that the orbits of the planets are ellipses, not circles, in order to keep the planets on track so that they would turn up where they're supposed to be at the right time, they had to have all these epicycles. These are mathematical constructions of circles within circles. And then you have the deferent, and then you have the equant. I won't go into any of those details, but I had to do a lot of mathematical jiggery-pokery to make planets turn up where you predicted they would turn up without too much difference between your predictions from these multiple epicycles and what you actually saw. So people played around with Copernicus's systems a bit. You also had the Indian astronomers, you had the Muslim astronomers, all doing their own thing, coming up with different ideas. So, for example, in the Almagest, Earth does not rotate. It sits there, everything rotates around it. But the number of other astronomers came up with the idea that Earth actually rotates for reasons that were not... It's very difficult to explain why they thought that the Earth would be either unmoving or rotating, because, amongst other things, they already worked out precession of the equinoxes. They knew that Earth would continually changing where it was pointing to in the sky, and it made sense if the Earth was rotating. It didn't make the same sort of sense if the Earth was rotating. But by having a non-rotating Earth, then you could have the outer shells of the solar system providing the motion for the inner shells of the solar system. Again, to us, in these days, that doesn't make a lot of sense. But back then, the concept of a premium mobile, of the heavenly material pushing all the other circles that had the planets in them, was a intellectually satisfying answer to why did the planets move in the first place. But as I said, people fiddled around with this a bit. There were a couple of people who came up with heliocentric systems. They weren't very popular. And then in 1614, a bloke called Simon Marius came up with a somewhat different view of the solar system. Again, you had Earth, the Moon, the Sun, and Venus and Mercury orbited the Sun. Now, this wasn't exactly the first time that it came up with, but it came up with at a time when Copernicus' heliocentric system was providing a better explanation for why Venus and Mercury didn't get very far from the Sun, because you had Sun, Venus, Mercury, Venus, then Earth, and we saw what we were seeing with Venus, Mercury not getting far from the Sun was a consequence of them orbiting the Sun and being seen from Earth far away. Now, there was a lot of argy-bargy around this, but Simon's system gave you an interesting approach. You had the outer planets doing what they were doing before, the Moon doing what it was doing before, and Mercury and Venus orbiting the Sun, completely sensible, and solved the puzzle of why Mercury and Venus didn't get very far from the Sun. It also had some advantages. It preserved, aside from preserving Earth at the centre, it meant that you could keep on using a lot of the same calculation methods to keep the system going. And then along comes Tycho. And Tycho then puts all the planets around the Sun, and it has the Sun and the Moon orbiting the Earth. Now, this preserved circular motion. This was a big thing. It preserved circular motion. One of the reasons that Copernicus, apart from naturally explaining why Venus and Mercury didn't get far from the Sun, he also got rid of the equant. Now, the equant, I can't really explain it very well, but the equant took away from the concept of circular motion. So I've already told you about epicycles. So epicycles were little circular motions of the planets around the greater circle that they orbited around. But to get the calculations correct, they had to add in an equant, which took away from perfect circular motion and made it far more complicated. Copernicus got rid of the equant, and he still had circular motion. He still had epicycles, but he had found a way to get the epicycles working without the equant. So everyone said, fantastic, this is really cool. But we still don't believe everything goes around the Earth, the Sun. Tycho put everything around the Sun. Fantastic, good. He shattered the crystal spheres. Now, the concept of the planets was they were moving in these spherical shells. They're often described as crystal spheres, but the crystal spheres were not crystals in any sense that we would think of, because they were not mundane matter. But they were nonetheless tangible material that carry the planets. Tycho shattered the crystal spheres. For his planetary system to work, the spheres had to intersect with each other, which could not happen if the spheres were some sort of sensible, tangible material. And so everyone went, hey, this is a really good system. It explains a whole lot. Explains why the planets, Mars and Venus and Mercury don't get far from the Sun. It keeps Earth at the center and doesn't have this weird jump from planet, Sun, planet around the Sun, then planet not around the Sun. It doesn't have that weird jump. So this is really good. This is really cool. Then along comes Galileo. He puts the Earth at the center again, does some calculations to make it a bit better than the original Copernican system, looks through his telescope and discovers the phases of Venus and Mercury. Now, you can't have phases of Venus and Mercury in the Ptolemaic system. You just can't. Well, actually, that's not true. You can have phases if you have the Venus and Mercury inside the sun, between the sun and the moon. You can have phases, but you can't have a crescent phase. You can go from gibbous to full, but you can't have crescent phases. Crescent phases killed the Ptolemy system dead, but you can still have crescent phases in both the Tychonian system and the Simon Marius system, because Venus and Mercury are orbiting the sun. What you needed then was a giant intellectual leap to get from this, is it going to be a Galilean Copernican system where you have phases of the moon, which completely wipes out the Ptolemy system, or you're going to have a Tycho system, which is actually just Copernicus' system inverted. It's a relatively approach to it, not very preserved the appearances, but it really made things a bit more complicated. And the things that you needed to distinguish between them required a range of technical issues that were not apparent at the time. Of course, everyone's ignoring Kepler. Kepler's worked out why you have the ratios of the orbits. He's worked out why the planets speed up and slow down during their orbit. He's got rid of all the epicycles and equinox with an elliptical orbit. It just falls out naturally, but it does have to go around the sun. So everyone's going, yeah, it's Tycho, Simon Marius, Galileo. Which one's right? What you needed was parallax, but you needed more than parallax. You needed two different kinds of parallax. So you needed stellar parallax was the obvious one. To dead eye alone, and with the telescopic instruments they had at the time of Galileo, parallax was still too small to be seen because the stars were very far away. Copernicus had already anticipated this, and he said that if the stars are very far away, then you won't see parallax. And Tycho said, okay, but if the stars are very far away, they have to be more than 7 times further than the sphere of Saturn. And he just couldn't come at that idea that the solar system was so big. So we'll leave it there, and I think we can talk about Kepler and his discoveries and how he discovered parallax for another time.
Well, thank you very much, Dr. Ian Astroblog Musgrave. Keep looking up.
I will indeed. And everyone else out there, keep looking up because there's lots of things to see.
Clear skies, Ian. Good night.
Good night, mate. You have a good time at the marathon, and all the best to your daughter.
And remember, Astrophiz is free, ad-free and unsponsored. Find us on astrophiz.com or your favourite social media platform. Keep looking up. Clear skies.
Radio Wave!